Hello everyone, here's the highlight video for this unit on heat. So here I have this animation of this gas molecules bouncing around here. Now, when you think about heat and temperature, I want you to think about energy. So what we could do is, if we were able to, is measure the velocity of every single molecule here, use 1/2 mv squared to get the kinetic energy of the whole system, and that could tell us how much energy is there. But it's just a very impractical way to calculate energy. So instead, we're going to use this idea of heat and temperature to help us do that. Similar thing for solids and liquids. There's also energy stored in the chemical bonds. And so there's going to be the kinetic energy of the vibration and the electrical potential energy in the chemical bonds. So when you think about heat and temperature, I want you to think about energy. This is how much energy is stored in the system. Now we have a lot of different units for temperature. Let's start with the one you're most familiar with, is Fahrenheit. So water freezes at 32, it boils at 212. And the coldest possible temperature is -460 degrees. Now, what do I mean by this? So when we lower the temperature of a gas, for instance, we're also lowering the energy. So how low can we go? Well, the lowest energy we can go is when those gas molecules no longer are moving. They're completely still. There's no kinetic energy left. Well, at that energy, the temperature of that substance is going to be -460 Fahrenheit. Similarly for Celsius, water freezes at 0 and boils at 100, so some nice numbers between these two. And the coldest possible temperature is -273. And our last one is Kelvin. They decided to move the 0 from freezing to the coldest possible temperature, but they kept the same increments between freezing and boiling. So there's a 100-degree increase in Celsius and a 100-degree increase in Kelvin. That's not true for Fahrenheit, though. What this means is a change in 1 degree Celsius is the same as a change in 1 degree Kelvin. But between Fahrenheit and Celsius and Kelvin, it's 5/9 or 9/5, depending on kind of which way that you go. So let's solve something here. So we want to convert from Fahrenheit into Kelvin. Well, we've got a bunch of different equations here that are also in your textbook. So we find Fahrenheit to Kelvin, and we just take that equation, and we can take our 70 and plug it right in here to the temperature in Fahrenheit. And that allows us to calculate what the temperature in Kelvin is going to be. In this case, 294.3 Kelvin. Now, something interesting happens when you increase the temperature of a solid. So if we look here, I have this metal rod of length L and it's at initial temperature T. Now, inside of this rod is a bunch of different atoms that are vibrating back and forth. So as you increase the temperature here, you're giving it more kinetic energy, right? There's more energy now. So these atoms are vibrating more energetically, meaning they're kind of pushing and bouncing off of each other more. What happens when we heat it up is because they're bouncing and vibrating more, those atoms actually spread out more. So they're farther apart now because they're kind of bouncing and pushing off each other more. So now we've heated it up by a certain amount of increased temperature, delta T. What that means is that it's also increased a length delta L. Now it's no longer. This isn't added on. Think about it, remember, like a rubber band kind of stretching out, okay? So there's an equation we can use to kind of solve for what this delta L is going to be. And that is called the thermal expansion equation. So that increase in length is equal to this alpha value, is the coefficient of linear expansion. And there's a big table in your book that will have a bunch of values for this. So each material, depending on the atoms that are in it and the chemical bonds between the atoms, this value is going to be very different. And this is the original length of our object, and this is the change in temperature. Now, it could be Kelvin or Celsius. Remember, a change in 1 degree Celsius is the same as a change in 1 degree Kelvin, so it doesn't matter. It makes it a little nice. And then I pulled some from your book. It's, here's the coefficient of linear expansion for aluminum, brass, and copper. You can see here. So let's do a problem. We have a steel bridge expansion joint allows the bridge deck to safely expand on hot days. So at 10 degrees Celsius, the steel beam is 20 meters long, but during the summer, the temperature rises to 40 degrees Celsius. And here we're told that the linear expansion for steel is this value here, 1.2 times 10 to the -5th. What is the new length at 40 degrees Celsius? So let's see what we're given here. We're given the coefficient expansion, the initial temperature of 10 degrees, the final temperature of 40 degrees, and the initial length of 20 meters. Well, we're going to need the change in temperature. So let's calculate that first. The change in temperature is the final minus initial, so it's gained 30 degrees Celsius. And then we can use our thermal expansion equation. Now, we know what alpha is, we know what L and delta T is. So alpha is that 1.2 value we were told before. The length is 20 meters and the change in temperature is 30. So we multiply those out and we get 7.2 times 10 to the negative fourth meters. But that's not the final length. That is just the change in length. So to get the final length, we add the change in length to the initial length. So the initial length is 20 meters. We add those two together, and this is our value for the final length of the bridge. Here are the equations that we used in this highlight video. I hope this helps.